Okay, we're shifting away from LMS type algorithms to a new one called the recursive least squares filter. So LMS, least mean squares, solved our normal equation, our Wiener-Hopf equation, Rxw is equal to Rdx, by inverting Rx. And in the case of LMS, we didn't have Rx, we didn't have Rdx, and we didn't want to do any inversion. So we solved by gradient descent, and we just used very noisy estimates of Rx and Rdx effectively. RLS, on the other hand, is going to solve W is equal to Rx inverse Rdx exactly, given our current estimates of Rx and Rdx. So it's going to have to deal with a few different things. So let's put those out there first so you can see where we're going with this. Just because we have a perfect solution based on our current estimates of Rx and Rdx does not mean we have a perfect estimate of Rx and Rdx yet. So it's going to have to deal with the fact that we may have a poor estimate or no estimate of those two values, and that our estimate may improve, giving us updated Rx and Rdx. Finally, to make this practical in any kind of real-world situation, we want to deal with non-stationary data. Okay, so those are our marching orders. We want to solve for the best filter. We want to do it perfectly, at least as perfectly as we can, because we're doing it perfectly based on poor estimates. But we also need to take into account non-stationary data. Well, let's talk about that last one first. Non-stationary data, if we're trying to take advantage of account for non-stationary data, then we can't have too long of a memory. We have to be able to update Rx and Rdx in such a way that from a long time ago, our estimate, the contribution of the data from a long time ago, does not meaningfully contribute to our current estimate. Okay, let's, what could we do? Well, we could brute force this. We could say, let's take the last P samples of data and use those to create an estimate of Rx and Rdx. And with that, we can simply invert Rx and multiply it by our Rdx estimate, and that would solve this problem that we've laid out. So I guess there's really one other thing that's implied but not stated, so let's go ahead and state it. It's the computational complexity of inverting Rx estimates every time they're updated. So let's see how this computational complexity plays out. Let's assume we had a filter of length p. We could solve for the ideal weights using gradient descent. So for gradient descent, we would have p² multiplications per iteration and on the order of p² adds per iteration. But also, we would have order np squared multiplies and adds to form Rx, and a bunch more for RDX. So even if we decided not to do gradient descent and just to do the inverse, then we have order p cubed operations for the inverse, but we still have to form our Rx and our RDX using these things down below. So then the next question is, well, how do we actually run this whole thing? So if this is a discussion of point number 4, then this will be a discussion of point number 1. That is, do we have to wait for n values to come in before we can estimate our Rx and our RDX? And then with point 2, what do we do if the signal changes? I guess this is point 2 and 3. Now, you know we've got a solution to this. But I want to set it up so you can see what's motivating this solution that we're going to propose. The recursive least squares title probably gives some of it away. And that is that we're going to start out with a poor estimate, and as we update R and RDX, we will iteratively improve our estimate, but we'll do it in such a way not like our gradient descent, which was a step in the right direction with each iteration. Instead, with these iterations, we will step directly to the new optimal solution. A few other things to point out, and then the next lecture we'll actually go into the derivation. One, we will minimize not the expected error, but the actual error. So this is somewhat similar to what we did with affine projection, and one of the reasons that we talked about that prior to bringing this in. So this is going to be the sum from I equals n to 0 of e squared I. We're actually going to modify this in a bit to make things a little bit more responsive as the signal characteristics change. And we're also going to define the data autocorrelation. So this is a new Rx. Now, one of the problems with having two different things defined with the same variables is, although context can usually tell you which one is which, it's important to remember that this is not the same as the expected value autocorrelation or the expected autocorrelation. So, first note that if we were actually trying to estimate the autocorrelation, we would have a 1 over n out front. And in this case, we don't. So that's one of the first big differences that we should note. Also note that it's a function of n. And as we get more values, we would expect that this is going to be similar to the real autocorrelation. So I've written it over here in a way to kind of drive this home, that this one, indexed by n, is actually equal to, as n gets large, the true autocorrelation, Rx, which is the expected value of x times x transpose, times n plus 1. So it's scaled differently, and it only approaches the true autocorrelation for a stationary sequence when n gets large. Okay, hopefully that's been enough warnings to put you on your guard, to always be careful when you see Rx from here on out. It turns out that the data autocorrelation is used in many signal processing things. One, because we never really have the true autocorrelation, and two, because this doesn't have the normalization, and often the normalization just goes away. So for example, with these two values for the data autocorrelation you see over here on the left, if we use those to solve for W, we would have Rx inverse and times RDX, the normalizing factor of n plus 1 would disappear. It would divide out. And so in this case, we now have the relationship Rxn Wn is equal to Rdx of n, and this value of W, if we solve for it, minimizes our error right there. Okay, so the advantages are that we're minimizing the actual error as we go along. The disadvantage, of course, is that there's a lot of computation, and that's what we're going to address in the next lecture.